During the Big Bang, matter and its oppositely charged counterpart, antimatter, were formed in equal amounts. When the two collided, they annihilated each other, disappearing and leaving behind only light. Yet, as the annihilation came to an end, some matter particles were left over. It was as if something had tipped the balance between matter and antimatter, resulting in the extra matter that went on to form the universe around us today. But what caused this imbalance? How is it that we and everything around us even exist? In 1967, Russian physicist Andrei Sakharov proposed that generating the matter-antimatter imbalance would have required the violation of one of the universe's fundamental symmetries, known as CP, or charge parity symmetry. Following Sakharov's statement, many physicists began searching for CP violating particles that would solve this mystery, and indeed some were successful, but not nearly enough CP violation was found to explain the imbalance. However, most recently, the T2K experiment in Japan had a major breakthrough. Strong evidence was found for CP violation in tiny particles known as neutrinos. The neutrino is an elementary particle that comes in three different types: the electron neutrino, the muon neutrino, and the tau neutrino. As neutrinos travel through space, they can shapeshift between these different types, allowing, say, an electron neutrino to morph into a muon neutrino and then back. It is this neutrino oscillation that physicists at T2K have found may violate CP symmetry. But how does CP symmetry work? In physics, a symmetry can be described as a transformation to a system that leaves the system completely unchanged. Say, rotational symmetry. If I take the Queen of Hearts and rotate it 180 degrees, it looks exactly the same, but if I do this with the Ace of Clubs, it appears quite different. In this case, rotational symmetry holds true for the Queen of Hearts, but for the Ace of Clubs, it's violated. However, unlike rotational symmetry, which involves one transformation, in order for charge parity symmetry to hold true, a particle must act exactly the same after undergoing two transformations: charge conjugation and parity inversion. Charge conjugation involves replacing a particle with its oppositely charged antiparticle, for example, replacing a negatively charged electron with a positively charged anti-electron, or in our case, replacing a neutrino with an antineutrino. Next is parity inversion. We can think of it as reflecting a particle through a mirror and then replacing the particle with its mirror image copy. To differentiate the two, we can characterize the particles as being either left-handed or right-handed. So say you take a left-handed neutrino and have it undergo both charge conjugation and parity inversion. The result is a right-handed antineutrino. In order for CP symmetry to be violated, these two particles must behave differently, and this is exactly what physicists at T2K found. On April 15, 2020, T2K published results showing that left-handed muon neutrinos seem to oscillate into left-handed electron neutrinos more often than right-handed muon antineutrinos oscillated into right-handed electron antineutrinos. And this was evidence for neutrino CP violation. The data from T2K supports the theory of leptogenesis, the idea that in the early universe, neutrinos could have indirectly tipped the scales between matter and antimatter, forming the matter-dominated universe that we live in today. This result is the next step down the path to understanding one of the greatest mysteries in modern physics. And with more data, we may finally be able to answer the question of how we and everything around us came to be.